So welcome everybody. Goedemiddag for the Dutch speaker. So today we're going to try to understand how large-scale distributed microservices they can be designed. And so I'm Luca, and I work actually for nearForm. I'm actually, you can find me on the internet with my name and my surname as an handle. And when I'm actually not working on architecture, I spend my time in the postmortem working group. So I've been working with crashing system for a while. I've been watching into core dumps, and now I'm busy building the system on top of Node that can analyze core dumps. But at the same time, I really have a dream. You know, it's not really nice to be called in the middle of the night that something is crashing. So what you want to do, you want to build resilient and scalable services with no maintenance. A little bit like the Roomba is the dream of every man. It's a simple machine. It goes through your house, and it does all the dust cleaning. Fantastic. Can save a lot of time. So let me tell you a little bit of a story, because without a story, it doesn't make sense. So once upon a time, there was this thing, and it's the monolith. So, and we all been through the transition on different kind of monolith. This one can be the famous Java monolith. And we all know that this one, it was not good, right? Thumbs down. So along the way of business and enterprise and, you know, also startups, the principle that Philip of Macedonia introduced, divide et impera, which means divide to rule. And that was the time that actually microservices, they landed in this magic world. And we all know, we are all working with Node, and we know that Node was born actually to support these kind of architectures. And microservices, they became hipster extremely fast. But the common understanding of microservices was that microservices were by definition stateless. But we all know that actually being stateless doesn't really mean being resilient. So how many of you are running Node microservices in production? OK. How many of you are using PagerDuty? OK. Only a few people. Wait until the phone call at 3 a.m. in the night, and you regret the day that you gave your phone number. And, you know, usually when company and ideas, they are coming to success, it means that a lot of people are using, a huge crowd is using your services. And so a lot of requests are hitting your services. And, you know, the common understanding on microservices is that you can horizontally scale them as much as you want. And that's actually what is going to happen. You turn your Amazon cloud or your own data center at the massive scale of Google. And that's why then you need Kubernetes and this kind of thing. But the truth is that the problem in a highly distributed system still stays the distribution. And distribution is a very complex system in a microservices environment. And I'm going to explain you the reason why. The problem is that we all arrived to build microservices with a fake promise that Amazon would bring us elasticity. And elasticity brings basically that horizontal scalability at almost no cost. Almost. And I mean, if you watch some of my talks, you know that I am not really the biggest friend of autoscaling and elastic load balancer, because I do believe that they are not really representing the correct way of scaling your services and your business logic and your functions for mass consuming. So this one, I think, is a beautiful picture. Apart having fantastic colors, this one is actually the magic world of containerization. So you have plenty of microservices, and because the security and isolation model that you want to implement in your microservices requires you to basically put them in a kind of isolated environment, and you basically create containers, and that's where Docker actually was the perfect fit with Node.js microservices. But actually still leaves a huge problem, and the huge problem is service discovery. So how many of you are familiar with the trouble of service discovery? Okay. How many of you regretted the day that microservices came in this world? Because I do almost every day that I need to solve the problem of service discovery. And the problem of service discovery is that you distribute your load, and then you centralize the resolution of your network topology in a monolith. I mean, without making names, we all know Console, HCD, they're monolith at the end. The problem of this model is that there's no resiliency, and the fault tolerance is very low. So, which means that basically you have this large-scale application, and a lot of people that are going to use it, and it's going to crash. And I can tell you that I heard a lot of people, and a lot of times, no, it's not going to crash. It's super resilient. I have try-catch everywhere. And at the end of the day, you end up basically miserably having to restore your application. And with restoring your application, there's always some kind of state that you need to restore. And state is something that, how many of you are familiar with Terraform or our infrastructure orchestration? Well, it's something that HashiCorp and Terraform, they solved, basically centralizing the state of the entire network topology in one single file and say, this one is how you represent all your infrastructure. And this one is basically the usual world of deploying distributed microservices. And there are some usual players, right? I mean, you can change them with different software, but I mean, everybody pushes some code. This code basically gets compiled into a Docker image. This Docker image, it ends up in the registry, and there is an orchestrator or a scheduler like Marathon that they distribute on a Mesos file system or a Mesos installation or whatever you want, ECS, Swarm. And the problem is that you always end up needing to register your application in a centralized storage that is Console. I mean, while you are in with all HashiCorp things, you put Console. And how many of you are familiar with Console, by the way? OK. The problem of the model of Console is that it works, but it still detects failure in your cluster through heartbeating. So heartbeating is it's a core principle of this distributed system. So there is a centralized system which is going to query and ping the different subsystems and say, are you still alive? Yes or no? And then it goes in what is called an unhealthy mode, and it's going to be disposed. And everybody knows that if you want to save money, you need to kill the machine. And you lose the core dump. But the problem stays that the state of your cluster, the health of your cluster might change at any time, at any condition of time, of the life cycle of your application. And that's where math and technology, they meet together. And how many of you have ever heard of SWIM? S-W-I-M. Great, then you're at the right talk. So SWIM is basically coming from a white paper written by some brilliant student of Cornell University. And is actually, for people that work in telecommunication, is nothing new. It's how actually most of cellular phones are working. But even easier, I hope Yunong is not here, but that's how most of the people that downloaded movie for a long time is concept of peer-to-peer. And SWIM actually, I think it's brilliant because its acronym says everything about what it's trying to solve. It's scalable, and so we can put a check, weakly consistent, infection style, membership protocol. Now I'm going to explain to you what these 4 letters they really mean in practice. So weakly consistent. The world is weakly consistent. So I always give this example to everybody. So how many of you have a bank account? I hope everybody. Okay. How many of you are receiving and making payment regularly? I hope everybody. Okay, good. So banks, which are regulating your transaction, they're weakly consistent. They're not strongly consistent. So in the moment that you make a transaction in your bank, the process of making this transaction strongly consistent against your balance is actually an offline process. So that's why if you try to transfer money from bank to bank of different, for example, provider, you end up actually getting your money the day after, because the mainframe has to reconcile all the transactions to be sure that the point-to-point transaction is valid. And if you build transactional system, this one is a core principle. And so your network has to be weakly consistent. You don't want to actually be on every transaction, check the state of every node in the network. You just want to say it might work. Failure detection is fundamental. If a node gets unhealthy, the entire network needs to answer to this problem. So what actually Swim is going to do is going to apply this concept, that is information dissemination. It's a very difficult word, just to say that every single node in your cluster is going to gossip to all the other nodes about the state. So you have basically a cluster of stateful machines, which is not bad, because at the end of the day, we are living in a stateful world that is time consistent, but is eventually consistent. You never know how something goes, right? Else everybody would play the lottery and it would be sure to win. And the most interesting part when you build a large-scale distributed system is that the workload is equally distributed across the cluster. Because the state is distributed, you can play very smart load balancing algorithms that are not round-robin anymore. So how many of you are familiar with Nginx round-robin algorithm or whatsoever, the ELB? Okay, just kill the ELB and your life gets much better. Basically, a gossip network is born for a distributed system. And how many of you are familiar with DynamoDB? Cassandra? Console? The same as before, I hope, of Console. These one are all distributed systems. So they all have a gossip protocol behind the scene to basically distribute the state across the cluster. Especially Console is built on top of Surf, that is another membership protocol. And this one sounds all magic, right? Because everything works. But there's still one thing that needs to be solved. And this thing, that is the big but, like always, that adding a node to the cluster, because you are scaling, brings the problem, how can I rebalance my topology? Because if the topology is fixed, it's very simple. It's a simple, plain, linear distribution. But as you add information and cluster nodes, there is a problem that is rebalancing. And that's where our best friend, the consistent hashing, comes in place. How many of you are familiar with the algorithm of consistent hashing? So Cassandra, Dynamo, they all use this principle. So just to make it very simple is that every time that you add a key in a shard key in the consistent hash string, so an hash, the entire hash gets rebalanced and gets reallocated. So imagine that you have a ring and you place something in a shard zone that is in between 1 and 3. That one is going to become the 2 p.m. shard zone. And it's kind of complicated to describe because the concept of a consistent hash string is that it's completely consistently rebalanced. And to make it very, very simple, imagine that every time that you put an information in the cluster is aware of where this particular information is located on the cluster because it shares the same hash key. So anybody ever played with partitioning in Oracle databases? Because I'm not a big fan of Oracle, but I think partition sharding on Oracle database is a masterpiece. So the thing is that you can add a lot of predictability to your elasticity because you know exactly where your information are going to be allocated and where are going to be distributed. And especially because, like we said, the state is going to be distributed across all the cluster. So we said about Surf, a clear example of a consistent hash string over a Swim protocol. And Node.js actually has some pretty smart implementation of these two things combined. One being ring pop from our best friend of Uber. Anybody working for Uber here? No, okay. It's basically a layer 7, so an application level sharding library. And Matteo Collina and me are working on a library called UpRing that is a simplified version of ring pop. Because ring pop, that is an application level sharding library that try to bring distribution in an eventually consistent world. So distribution needs to be strongly consistent, but we said that the world is eventually consistent. Basically, try to solve on large scale this problem. That is application partitioning. So imagine that you are requesting for some user information and you have a cluster that can answer to this information. What ring pop and UpRing they're trying to do, they are basically telling in-app, look that you will basically find this information at this particular node shard. In order to make all this thing work, there is one of the famous secrets of Fatima, that is hyperbahn. It's a mystery how it really works, but it's basically an overlay network on top of a consistent hash ring. And why do they need routing and so an overlay network on top of a consistent hash ring? Well, it's because they needed to solve the problem of service discovery on a scale of millions of events on their API per second. And the cluster grows elastically, insanely. Something that Consul, for example, cannot really do at scale. You know, if anybody of you runs Consul with a registrar, that's the usual way of running basically kind of low volume distribute architecture. So one of the core principles on how Uber can basically dispatch so many information across their cluster is actually that they decided to create their own protocol that is a multiplexer. So it's a network multiplexing and framing protocol based on TCP. And what it does is basically the problem of a distributed system is always time, right? It's concurrency. And what they do, they basically have ring pop to distribute the state and the information, the hyperbahn to shield the service discovery part. And in order to make communication time consistent, they build their own multiplexing protocol on top of TCP. And they use pure RPC function, and that's a very interesting decision in distributed architecture. Because at the end of the day, if you have an HTTP service, inside of a distributed system is still a function that you're trying to call. And one of the clear example nowadays on the market is Lambda. Is anybody using Lambda with the API gateway? Okay, basically the problem that a lot of large-scale enterprises are trying to solve is what Uber already solved, right? What they want to do, they want to stay away from Lambda because they don't have control. And the massive control that this library can give, they allow that to have extreme monitoring, traceability, auditability, that are all problem and non-functional requirements of a highly distributed system that process basically financial transaction in case of Uber. And so one of the things that we all hear is that the serverless architecture. And serverless architecture, they are based on top of this principle. So services, they are dynamically added to a cluster. They are represented not anymore as a HTTP endpoint, but as basically RPC function that are called through TCP. And so how many of you, by the way, are running serverless architecture? Not a lot. None. So serverless is basically trying to kill what is the DevOps hell. And if you think about what we saw before about distributing on a cluster and in an infrastructure containers, that's actually entering what is called the DevOps hell, right? Because it's complex, it's difficult to make it consistent. And you know, what is actually right now extremely hipster is to hear the world of serverless application. But if you think about this massive scale, so we're talking about millions of requests per second. One very interesting thing is that if you think at function distribution on a cluster, so if you think that your business logic is just a function distributed on a cluster, you basically already enter the future where you abstract the complexity of scaling your network. That is actually the problem that microservices introduced in the beginning. And if you really want to know a little bit more how this thing all works, it takes more than 20 minutes to explain how to implement it. But you can book a clinic at the nearForm booth, and I will be more than happy of showing you some clear example. It's never good to make a demo on stage. And I thank you for entering the magic world of gossip protocol and consistent hashing. So I hope you are starting to use upring or any consistent hashing library to scale your application at massive scale. Thanks.